Gravity is not a force. That sentence would have sounded like nonsense a few years ago, and it may turn out to be the most important thing physics has learned about gravity in a century. Every second of your life, something has held you to the ground, steady and certain. The first rule any of us ever learns. But when physicists tried to fit that pull into the same quantum rules that explain light and atoms and everything else, it refused, again and again, for 100 years. And a new paper suggests the reason is far stranger than anyone wanted to believe. Gravity may not be a basic ingredient of reality at all. It may be something the universe does while keeping track of information it never shows you, the same way the warmth of a room is really just the motion of molecules you cannot see. The floor you have trusted your whole life may be a surface stretched over something deeper. Get comfortable and settle in. Hit subscribe if you're new here, because by the end of this, the weight of your own body is going to feel like a message from a layer of reality you have never seen. Now, let's slowly ease into this. Part 1. The one force that refuses to fit. Hold your hand out in front of you and let something small rest in your palm. A coin, a key, a folded piece of paper. Now open your fingers and let it go. It falls. You knew it would fall before you opened your hand, and that certainty is one of the oldest, steadiest things a human being can feel. Gravity is the first physics any of us ever learns, long before we have a word for it. A baby drops a spoon from a high chair, again and again, and learns the most reliable rule in the universe. Things fall. The ground waits below. Nothing you have ever experienced has contradicted this, not once, across your entire life. So it might come as a surprise to learn that gravity is the single greatest embarrassment in modern physics. It is the force we understand least, the one that refuses to sit down at the same table as everything else, the one that has quietly resisted a century of the smartest people alive. The thing you trust most is the thing physics can least explain. To feel why, we have to talk about the other forces, the ones you rarely think about, because they never announce themselves the way gravity does. Physics, as we currently understand it, is built out of 4 fundamental forces. There is electromagnetism, which is responsible for light, for electricity, for the fact that your chair pushes back against you, instead of letting you sink through it. There is the strong nuclear force, which glues the cores of atoms together against every instinct those particles have to fly apart. There is the weak nuclear force, which governs certain kinds of radioactive decay and quietly runs the furnace at the center of the sun. And there is gravity, the pull between anything that has mass or energy, the force that shapes planets and stars and the largest structures in existence. 3 of those 4 forces share something remarkable. Over the course of the 20th century, physicists learned to describe electromagnetism, the strong force and the weak force, in a single, unified mathematical language. That language is called quantum field theory, and it is, without exaggeration, the most successful description of nature humans have ever produced. In this picture, each force is carried by particles. Electromagnetism is carried by the photon, the particle of light. The strong force is carried by particles called gluons. The weak force is carried by heavy particles with unglamorous names. Each of these was predicted on paper and then found in experiments, sometimes decades later, exactly where the mathematics said it would be. The precision here is almost uncomfortable. Some predictions of quantum field theory have been confirmed to more than 10 decimal places. That is like predicting the distance between 2 cities and being correct down to the width of a single human hair. Now here is the quiet scandal. Gravity does not fit into that language. It never has. Every attempt to write gravity in the same quantum form that worked so beautifully for the other 3 forces has ended in failure. Not a small failure, not a rounding error, but a complete collapse. When physicists try to calculate what gravity should do at very small distances and very high energies, the equations stop producing numbers and start producing infinity. Every quantity they want to compute blows up, endlessly, uncontrollably. The mathematics does not merely get hard, it stops meaning anything at all. For a long time, the assumption was that this was a temporary problem, a technical wall that a clever enough person would eventually climb. The other forces had been stubborn too, before the right ideas arrived. Surely gravity was the same. Surely there was a particle waiting to be found. A graviton, the gravitational cousin of the photon. And once we understood it properly, gravity would slot into place alongside its three siblings, and physics would finally be whole. Generations of theorists have poured their careers into that hope. String theory, loop quantum gravity, and a dozen other frameworks were built in large part to solve exactly this one problem. And for all their beauty, none of them has closed the case. Gravity is still standing apart, still refusing, still the exception. This is the point where most explanations of gravity stop, with a shrug and a promise that someday we will figure it out. But there is another possibility, one that has been growing slowly in the background of physics for 50 years, and it is far stranger than a missing particle. What if the reason gravity refuses to become a quantum theory is not that we have been too slow or too foolish? What if gravity refuses because it is not that kind of thing at all? What if we have spent 100 years trying to break gravity down into its smallest pieces, and the reason we keep failing is that gravity has no smallest pieces, because gravity is not fundamental in the first place? That is the idea a new paper has put back at the center of physics, with the mathematics finally in place. The claim is that gravity is not a basic force of nature, not one of the ground floor ingredients of reality. Instead, gravity is something that emerges from a deeper layer, the way the warmth of a room emerges from the motion of countless invisible molecules, the way the pressure of the air in this room is not a fundamental thing, but a summary of trillions of tiny collisions you never feel individually. On this view, gravity is a kind of bookkeeping. It is what the universe does when it keeps track of information, and the pull you feel right now is the large-scale shadow of a ledger you can never directly read. If that sounds like a wild leap, hold on to your skepticism, because we are going to earn every step of it. We are going to walk the actual path physicists took, starting with a young graduate student in the 1970s who noticed something impossible about black holes, moving through a single overlooked paper from 1995 that should have shaken the world and mostly did not, and arriving at a recent result that finally names what the whole thing has been about. Along the way, the most familiar sensation you have, the feeling of your own weight pressing down into whatever is holding you up, is going to become one of the most mysterious things in the cosmos. Because here is what the new work is really saying, underneath the equations. For 100 years we have treated gravity as bedrock, as the deepest and most solid floor of physics, the thing everything else rests on. And the more carefully we look, the more that floor seems to be a surface. Underneath the most fundamental seeming force in the universe, there is a hint of something more fundamental still, something made not of particles or energy, but of information and entropy, of the sheer number of ways the universe could be arranged when you are not looking closely enough to tell the difference. Einstein gave us the most beautiful description of gravity ever written. It has never once been wrong, and yet, as we are about to see, it may have been describing the surface of something without ever telling us what lay beneath. So let us begin where the trouble begins, with a theory so successful that its single greatest flaw went almost unnoticed for 100 years. Let us begin with what Einstein gave us, and with the one question he never answered. Part 2. Einstein's Beautiful Silence. In 1915, after nearly a decade of struggle, Albert Einstein finished the work that would define the rest of physics. He called it the general theory of relativity, and it replaced an idea of gravity that had stood, almost unchallenged, since Isaac Newton. Newton had given us gravity as a force, an invisible pull reaching across empty space between any two objects with mass. It worked astonishingly well. It sent predictions of planetary motion into the record books and held up for more than 2 centuries. But Newton himself was uneasy about it. How, he wondered, could two objects pull on each other across millions of miles of nothing, with no rope between them, no contact, no mechanism? He admitted, in a famous letter, that he could not say what gravity actually was. He could only say what it did. Einstein's answer was to throw out the idea of a pull entirely. There is no force reaching across space, he said. Instead, there is spacetime, the combined fabric of the 3 dimensions of space and the 1 dimension of time, woven together into a single flexible thing. And matter and energy bend that fabric. Place a massive object anywhere, a star, a planet, your own body, and the space-time around it curves. Other objects, moving through that curved space-time, simply follow the straightest possible path available to them. What looks like a pull is really just motion along a curve. The moon is not being yanked toward the Earth by an invisible cord. The moon is coasting in a straight line through a region of space-time that the Earth has bent into a circle. This is one of the most beautiful ideas in the history of thought, and it is worth sitting with how strange it is. When you stand on the ground, you feel gravity pulling you down. But in Einstein's picture, there is no downward pull at all. The ground is pushing you up. Left to yourself, you would follow the natural curve of space-time, which is to say, you would fall freely, weightless, the way an astronaut floats. The only reason you feel heavy is that the solid Earth is in the way, constantly shoving you off your natural path. Your weight is not the feeling of gravity pulling you. It is the feeling of the floor refusing to let you fall. Gravity, in Einstein's hands, stopped being a force and became the shape of reality itself. And the theory delivered. In 1919, astronomers watched starlight bend as it passed the sun during a total eclipse, curving by exactly the amount Einstein's equations predicted, and he became world famous overnight. The theory explained a wobble in the orbit of Mercury that had baffled astronomers for decades. It predicted that time itself runs slower deeper in a gravitational well, a prediction so precise that the satellites in the global positioning system in your phone have to correct for it constantly. If they did not, your navigation would drift by kilometers within a day. General relativity predicted black holes, regions where the curvature becomes so extreme that nothing can escape, and we have now photographed them. It predicted gravitational waves, ripples in space-time itself, spreading out from violent cosmic collisions, and in 2015, exactly 100 years after the theory was published, we detected them directly, feeling a wave from 2 black holes that merged more than 1 billion years ago, stretch and squeeze our instruments by less than the width of a proton. In more than a century of increasingly brutal testing, general relativity has never once been caught being wrong. It is worth lingering on one consequence of this before we move on, because it will matter enormously later. Einstein realized that a person in free fall feels no gravity at all. An astronaut in orbit is not beyond the reach of the Earth's gravity, not by a long way, since the Earth's pull at that altitude is nearly as strong as it is on the ground. The astronaut floats simply because they are falling freely, coasting along the natural curve of space-time, with nothing pushing them off it. Fall freely, and gravity vanishes from your experience entirely. Feel weight, and it is because something, the floor, the seat, the ground, is stopping your fall and shoving you off your natural path. Einstein elevated this observation into a principle, the idea that being at rest in a gravitational field and accelerating through empty space are physically the same situation, indistinguishable from inside a sealed room. A person in a windowless box cannot tell whether the box is sitting on the Earth or being accelerated through deep space by a rocket, because in both cases they feel exactly the same downward push. This equivalence between gravity and acceleration is one of the pillars the whole theory rests on, and it is the reason that, much later in our story, the strange warmth that an accelerating observer feels in empty space will turn out to have something to say about the ordinary weight you feel sitting still. So you might reasonably ask what more we could possibly want. If the theory works perfectly, if it passes every test, what is the problem? And the answer is subtle, and it took physicists a long time to feel its full weight. The problem is not that general relativity is wrong. The problem is that general relativity does not explain itself. Think carefully about what the theory actually tells you. At its core is a single compact equation, one of the most famous in all of science, which relates the curvature of space-time on one side to the matter and energy present on the other. Put a certain amount of matter and energy in a region, and the equation tells you exactly how much the space-time there will curve. It is a precise, reliable, perfect instruction, but it is only an instruction. It tells you that matter curves space-time, and it tells you by how much, and it never, ever tells you why. Why should the presence of energy bend the geometry of the universe at all? Why this much curvature and not more or less? Why should space-time be the kind of thing that can be bent by matter in the first place? Einstein's equation is silent on every one of these questions. It hands you the rule and walks away. This is the thing to hold on to for the rest of our journey, so let me put it as plainly as I can. General relativity is a rule book, not a reason. It tells you what gravity does with breathtaking accuracy, and it tells you nothing about what gravity is or where it comes from. It is like being handed a book that perfectly describes how a magician's trick unfolds, every move, every timing, every result, without a single word about how the trick actually works. You could use that book to predict the trick flawlessly, forever, and still have no idea what was really going on behind it. For most of the 20th century, physicists were happy to live with the rulebook. The theory worked, and there were other mysteries to chase. But there is a particular kind of discomfort that comes from having a description without an explanation, and it grows over time. Because a rule that comes from nowhere is a rule you do not fully trust. If you do not know why matter curves space-time, then you do not really know whether that rule holds everywhere, in every extreme, at the beginning of the universe, or inside a black hole, where the theory itself predicts its own breakdown. An unexplained law is a law standing on air. There is a useful comparison here from the history of a completely different subject. For a long time, people understood the behavior of gases through a set of laws that connected pressure, volume, and temperature. Heat a sealed container, and the pressure rises. Squeeze a gas into half the space, and, at the same temperature, its pressure doubles. These laws were reliable, they were precise, and they were used to build engines that changed the world. And for a while, nobody knew why they were true. They were rules that worked, handed down from experiment, standing on air. Then, in the 1800s, a handful of physicists realized that a gas is made of countless tiny molecules bouncing around, and that pressure is nothing more than the drumbeat of those molecules striking the walls of the container, and temperature is nothing more than how fast they are moving on average. Suddenly the rulebook had a reason. The gas laws were not fundamental at all. They were a large-scale summary of the frantic motion of things too small to see. The explanation had been hiding one level down in the statistics of the invisible. Keep that story in your mind, because it is going to happen again, and the second time it happens, the thing being explained will not be a canister of gas. It will be gravity itself, and space-time, and the shape of the universe. For now, simply notice the shape of the puzzle. We have a perfect rulebook for gravity, and no reason behind it. And in physics, whenever you find a rule that works perfectly, but has no explanation, history whispers the same suggestion. Look one level down. Something smaller is keeping the books. The first person to hear that whisper clearly in the context of gravity, was not thinking about apples or planets at all. He was thinking about the strangest objects in the universe, objects that should have had nothing to do with heat, and he noticed that they were warm. Part 3. Heat where it doesn't belong. To understand what happened next, you need to know a little about entropy, which is one of those words that gets thrown around so often it has lost most of its meaning. People say entropy is disorder, or that entropy is the tendency of things to fall apart. And those descriptions are not exactly wrong, but they miss the real idea. Entropy is about counting. It is a measure of how many different ways the small pieces of a system could be arranged while the system, viewed from the outside, looks exactly the same. Picture a deck of cards. There is only one arrangement that counts as perfectly sorted, every suit in order, ace through king, but there are an astronomical number of arrangements that count as shuffled, because when you glance at a shuffled deck, one random order looks much like any other. A sorted deck has low entropy, because very few arrangements qualify as sorted. A shuffled deck has high entropy, because a staggering number of arrangements qualify as shuffled. This is why shuffling a sorted deck almost always destroys the order, and why you never see it happen in reverse. There are simply so many more ways to be messy than to be neat that randomness carries you toward the messy states every time. That relentless drift, from the few arrangements to the many, is the second law of thermodynamics, the closest thing physics has to an unbreakable commandment. Entropy, in any closed system, tends to increase and essentially never decreases. Entropy is deeply tied to information, and this is the connection that will matter most. The entropy of a system measures how much you do not know about its exact internal arrangement. A low entropy system is one you know a lot about, because there are few possibilities to consider. A high entropy system is one you know little about, because there are countless possibilities hidden behind the same outer appearance. Entropy is missing information, made into a number. There is one more feature of entropy worth making vivid, because it will become the strangest clue in the entire story. Entropy is not a property of the small pieces themselves. It is a property of how much you, the outside observer, cannot see. A single molecule has no entropy of its own. Entropy only appears when there is a gap between the coarse, blurry description you can access from outside and the fine, exact arrangement hidden within. This means entropy is not quite a thing in the world in the way that mass or charge is a thing in the world. It is a thing about the relationship between the world and an observer who cannot track every detail. It lives on the boundary between what is and what is known. That may sound like a philosophical nicety, but keep it close, because when entropy shows up attached to gravity, it will drag this strange observer dependence along with it, and the question of whose ledger the universe is keeping will turn out to have no simple answer. Now, for 2 centuries, entropy and temperature and heat lived comfortably in one corner of physics, the study of gases and engines and warm objects cooling down. And gravity lived in a completely different corner, the study of orbits and falling bodies and the curvature of spacetime. These 2 subjects had nothing to do with each other. Thermodynamics was about the jostling of molecules. Gravity was about the silent geometry of the cosmos. No one expected them ever to meet. Then came black holes, and the border between the 2 worlds began to dissolve. A black hole, in Einstein's theory, is the purest object imaginable. It is a region where matter has collapsed so completely that the curvature of spacetime becomes overwhelming, and a boundary forms around it, called the event horizon. Cross that boundary, and you can never return, never send a signal back, never escape, no matter how fast you move, because escaping would require moving faster than light, and nothing can. The event horizon is not a physical surface. There is nothing there to touch. It is simply the line in space, beyond which the future leads only inward. And according to general relativity, a black hole is described by almost nothing at all. Give me its mass, its spin, and its electric charge, and I can tell you everything there is to know about it. This is sometimes called the idea that black holes have no hair, meaning no extra features, no personality, no detail. Two black holes with the same mass, spin, and charge are perfectly, absolutely identical. A black hole is about as simple as an object can be, which is exactly why what happened in the early 1970s was so disturbing, because a young physicist looked at these austere, featureless objects and became convinced that they had to have an entropy. And an object with entropy is not simple at all. An object with entropy is hiding an enormous amount of information behind its plain exterior. The reasoning came from a paradox. Entropy, remember, always increases. It is the one law you cannot cheat. But imagine you take a cup of hot tea, which has a good deal of entropy in the frantic motion of its molecules, and you drop it into a black hole. The tea is gone. It has vanished past the event horizon, beyond all possible observation. So where did its entropy go? If the black hole has no entropy of its own, then the entropy of the tea has simply been erased from the universe, and the total entropy of everything has gone down. You would have found a way to break the second law of thermodynamics with nothing more than a black hole and a cup of tea. You could clean up the entire universe, tidy it endlessly, just by feeding your mess into the dark. That could not be allowed. The second law is too central, too load-bearing, to be defeated so cheaply. And so the young physicist reasoned that the black hole must absorb the entropy of whatever falls in. The entropy is not destroyed. It is added to the black hole's own hidden account. The black hole must have an entropy, and when you drop the tea in, the black hole's entropy must go up by at least as much as the tea's entropy went away. The books have to balance, even here, even at the edge of the darkest object in existence. And then came the part that should have stopped physics in its tracks. When the mathematics was worked out, the entropy of a black hole turned out to be proportional not to its volume, not to how much space it contains, but to the area of its event horizon, the size of its surface. This is genuinely bizarre. For every ordinary thing you have ever encountered, the amount of stuff it can hold, the amount of information it can store, grows with its volume. A larger box holds more. A bigger hard drive stores more. Double the space inside, and you double the capacity. But a black hole breaks this rule completely. Its capacity for entropy, its hidden information, grows with its surface area alone, as if everything the black hole had swallowed was somehow written on its outer boundary rather than stored in its interior. The information is on the surface, not in the bulk. Hold that oddity too. It is going to return as one of the biggest clues in this entire story. But there was still a serious problem with the idea, and the person who pointed it out most forcefully was Stephen Hawking. Because here is the thing about entropy and temperature. In physics, they come as a package. If an object genuinely has entropy, then it must also have a temperature. And if it has a temperature that is above absolute zero, then it must radiate. Everything with a temperature glows, in some form, whether the warm infrared of your own body, or the visible light of a fire, or the searing white of a star. That is not optional. It is one of the oldest results in the study of heat. So if a black hole truly has an entropy, and therefore a temperature, then a black hole must glow. It must give off radiation. It must, in some slow and quiet way, be warm. And that seemed completely absurd. The entire definition of a black hole is that nothing escapes it. Nothing gets out. A black hole is, by construction, the coldest and darkest thing that can exist. A perfect trap from which not a single ray of light can flee. To say a black hole radiates is to contradict the one property everyone agreed it had. Gravity, in the form of these objects made of pure curved spacetime, has no business being warm. Heat belongs to gases and engines and jostling molecules, not to the silent geometry of a collapsed star. Temperature had wandered into a place it did not belong, and it refused to leave. Hawking set out to prove the whole idea wrong. He was going to show, with careful quantum mathematics, that a black hole has no temperature, that it does not radiate, that this talk of black hole entropy was a mistake. He was one of the finest minds in the field, and he was annoyed, and he went looking for the error. What he found instead was one of the most important results in the history of physics, and it was the opposite of what he wanted to find. Part 4. The heresy becomes fact. Let us slow down here and stand inside the moment, because this is one of those rare turning points where you can almost feel the ground shift under a whole field of science. It is the early 1970s. Picture a young graduate student named Jacob Bekenstein working under the legendary physicist John Wheeler at Princeton. Wheeler is the man who popularized the very phrase black hole, and he has a habit of tossing out unsettling ideas to his students and watching what they do. One day he says something that will not leave Bekenstein alone. He points out that whenever a hot object falls into a black hole, its entropy seems to disappear from the universe, and that this feels like a crime against the second law of thermodynamics. Bekenstein takes the problem and carries it with him for months. He fills notebooks. He becomes convinced, against the intuition of nearly everyone around him, that the only way to save the second law is to grant the black hole an entropy of its own, an entropy written on the area of its horizon. When he says this out loud, most senior physicists think he is simply confused. A black hole is geometry. Geometry does not have entropy. The idea sounds like a category error, like asking how much a triangle weighs. Now shift across the ocean to Cambridge, where Stephen Hawking, already one of the most formidable theorists alive, hears about Bekenstein's claim and does not like it. To Hawking it looks not just wrong but sloppy, a misuse of a beautiful theory. He decides to settle the matter by doing the calculation properly, by bringing the full machinery of quantum physics to bear on the region just outside a black hole's horizon, where empty space is not truly empty but seethes with quantum activity. He expects to find that nothing comes out, that the black hole stays perfectly dark, that Bekenstein's entropy was a fantasy, and now the scene itself. The chalk dust hangs in the light. Hawking bends over the equations describing the quantum vacuum at the very lip of the horizon, that razor-thin boundary between the universe and the place of no return. In the vacuum, pairs of particles are constantly flickering into being and annihilating back into nothing, borrowing energy for the briefest instant the laws allow. He follows what happens to these pairs when they appear right at the edge. One partner falls inward, across the horizon, lost forever. The other is left outside, suddenly alone, its partner gone, and with nothing to annihilate against, it escapes, carrying energy away from the black hole. He checks it, and checks it again, looking for the mistake he is certain is there. There is no mistake. The mathematics is unambiguous, and it is telling him the impossible. The black hole is glowing. A faint, steady stream of particles is leaking out of the darkest object in the universe. Radiation with a real temperature. Radiation that means the black hole is slowly, unbelievably, evaporating. He has set out to bury Bekenstein's idea, and has instead handed it the one thing it lacked. The number that comes out of his quantum calculation for the entropy matches Bekenstein's guess exactly, down to the factor of 1/4. He has proven his rival right. That radiation is now called Hawking radiation, and the year is 1974, and physics has never been the same since. What Bekenstein proposed on the strength of a stubborn intuition, Hawking confirmed with the full weight of quantum mathematics, reluctantly, almost against his will. Together, their names are now permanently joined in the formula for black hole entropy, one of the most quietly revolutionary equations ever written. And it is worth pausing on how genuinely radical this was, because half a century of familiarity has dulled it. Two completely separate provinces of physics, thermodynamics, and gravity, which had spent their entire histories ignoring each other, suddenly turned out to be describing the same object with the same numbers. A black hole, made of nothing but curved empty spacetime, with no molecules, no gas, no moving parts of any obvious kind, has a temperature. It has an entropy. It obeys the laws of heat. You can write down the rules for how black holes behave, and they line up, term for term, with the laws of thermodynamics that were worked out by people studying steam engines in the 1800s. The correspondence is not loose or poetic. It is exact. Where the laws of thermodynamics talk about temperature, the black hole laws talk about the strength of gravity at the horizon. Where thermodynamics talks about entropy, the black hole laws talk about the area of the horizon. Where thermodynamics forbids entropy from decreasing, the black hole laws forbid the horizon area from shrinking. That last one turned out to have a spectacular real-world consequence. Because entropy can never decrease, and the entropy of a black hole is its horizon area, the total area of black hole horizons can never decrease either. So when two black holes crash together and merge, the surface area of the final combined black hole must always be larger than the two original surfaces added together. This is not a philosophical claim. It is a hard prediction. And in the years since we began detecting gravitational waves from black hole mergers, we have been able to check it. We measure the sizes of the two black holes before they collide, and the size of the one they become, and the area law holds. The horizon of the merged black hole is bigger, exactly as the marriage of thermodynamics and gravity demands. Heat, which had no business being anywhere near these objects, is quietly running the show. So by the middle of the 1970s, physics was holding a clue it did not know what to do with. Black holes are thermodynamic objects. They have temperature and entropy. Gravity and heat are somehow, secretly, the same subject. But almost everyone treated this as a curiosity confined to black holes. A strange feature of these particular extreme objects. Interesting, but isolated. Black holes were exotic, far away. Nothing like the ordinary gravity that holds you in your chair. Surely this thermodynamic behavior was just a quirk of the most extreme gravity in the universe, and had nothing to say about gravity in general. That assumption felt safe. It was also, as we are about to see, completely wrong. The connection between gravity and thermodynamics was not a special feature of black holes. It was a feature of gravity itself, everywhere, in every falling apple and every orbiting moon. And it would take one more physicist, working alone with a piece of astonishingly simple reasoning, to drag that truth out into the open. He would take the thermodynamics that Bekenstein and Hawking had found at the edge of a black hole and show that it applies at every point in empty space, including the space you are sitting in right now. And when he did, Einstein's great equation, the rulebook for gravity itself, would fall out of the mathematics of heat, as though it had been hiding there the whole time. Before we go there, hold on to the strangeness of where we already are. We started with the most ordinary thing in the world, the fall of a dropped object, and we have arrived at black holes that glow in the dark and obey the laws of steam engines. We have learned that the simplest objects in the universe are secretly hiding oceans of information on their surfaces. And we have a growing suspicion, still unproven, still waiting for its moment, that heat and gravity are two faces of one thing. The question that Bekenstein and Hawking left hanging, the question that would haunt the next 50 years of physics, was almost childlike in its simplicity, and no one could answer it. If a black hole has an entropy, and entropy is always a measure of hidden information, of the countless arrangements of something too small to see, then what exactly is being counted? The entropy of a black hole is the entropy of what? Part 5. Coincidence or clue? For a long time, the connection between gravity and thermodynamics sat in the literature like a beautiful stone that no one knew how to set. It was admired, it was cited, and it was, for the most part, quarantined. Black holes have entropy, physicists agreed, and then they mostly went back to work on other things, because it was not clear what the fact was supposed to mean. There are two ways to react when two unrelated parts of your understanding suddenly line up. The first is to call it a coincidence, a mathematical accident, a case where the same equations happen to describe two different things for reasons that are ultimately shallow. This happens more often than you might think. The mathematics of a swinging pendulum looks a lot like the mathematics of an electrical circuit, but no one believes a pendulum is secretly an electrical circuit. Sometimes similar equations are just similar equations. The second reaction is to suspect that the resemblance is not an accident at all, but a signpost pointing at something you have not yet understood. Sometimes two things obey the same laws, because they are, at bottom, the same kind of thing. When the 18th century laws of gases turned out to match the statistics of moving molecules, that was not a coincidence. It was a revelation. The gas laws match the molecular statistics, because a gas simply is a crowd of molecules, and its laws are their statistics written large. So which was it for gravity and heat? Was the thermodynamic behavior of black holes a mathematical fluke, a surface resemblance with nothing underneath? Or was it the first visible edge of a much larger truth, the truth that gravity and thermodynamics match because they are, somehow, the same subject? For years, the honest answer was that nobody knew, and reasonable physicists disagreed. But the more people stared at the black hole entropy formula, the harder it became to believe in coincidence. And the reason was that the formula was too specific and too deep. It did not just say black holes have some entropy. It tied that entropy to the area of the horizon in a precise way, and it wove together, in a single short expression, the constants that govern three entirely separate domains of physics. There is the constant that governs gravity, which comes from Newton and Einstein. There is the constant that governs quantum mechanics, which comes from the world of the very small. And there is the constant that governs thermodynamics, which comes from the study of heat. Three great pillars of physics, three fields that developed independently over centuries, all appearing together in one tidy formula for the entropy of a black hole. When constants from that many different worlds show up in the same equation, physicists get a particular feeling in the pit of the stomach. It means these worlds are not really separate. It means something underneath is tying them together, and you are seeing the knot without yet seeing the rope. This is the moment to name a thought that has been gathering quietly beneath everything we have said, because it is the emotional core of this entire story, and it is genuinely unsettling once you let it land. For all of history, we have treated gravity as bedrock. It is the deepest flaw of physics, the force that shapes the largest things, the oldest and most reliable feature of the universe. When we imagine the fundamental ingredients of reality, gravity is always on the list, alongside the particles and the other forces. It is one of the things everything else is supposed to rest upon. That is what fundamental means. It is where the explanations stop, the ground beneath which there is nothing deeper. But the thermodynamic behavior of black holes whispers a different story. Entropy is never fundamental. Entropy is always, without exception, a signal that you are looking at the large-scale behavior of many smaller things you are not tracking individually. Temperature is never fundamental either. A single molecule has no temperature. Temperature only exists when you stop following each molecule and start summarizing the crowd. So if gravity carries an entropy, if gravity has a temperature, then gravity is showing every symptom of being a large-scale summary of something smaller. And a summary is not the bottom. A summary is a surface. Sit with what that would mean. It would mean that the most fundamental seeming force in the universe is not fundamental at all. It would mean that gravity is a symptom, not a cause. It would mean that the floor we have all been standing on, the solid bottom of physics, is actually a lid, and that beneath it lies another layer we have never seen, a layer of countless small things whose bookkeeping we experience as the curve of spacetime and the fall of a stone. The thing we thought was the ground turns out to be a ceiling for something below. That is a vertiginous thought, and it is worth being honest that in the 1970s and 80s, it was only a suspicion, a feeling in the mathematics, not a proof. You could look at the black hole entropy formula and read it two ways. You could say, gravity behaves thermodynamically because black holes are special objects where quantum effects and gravity happen to overlap. Or you could say, Gravity behaves thermodynamically because gravity is thermodynamics, always and everywhere, and black holes are simply the place where the truth becomes impossible to ignore. The formula alone could not decide between those readings. It was a clue, not a verdict. What was needed was someone willing to take the second reading seriously and push it as far as it would go. Someone willing to say, out loud, that if gravity really is thermodynamics, then the connection should not be confined to black holes. It should show up everywhere. It should be possible to stand at any point in empty space, anywhere in the universe, far from any black hole, and find the same thermodynamic bookkeeping quietly at work. And if you did that, if you applied the laws of heat to ordinary space itself, then something extraordinary ought to happen. The rule book of gravity, Einstein's great equation, the thing he handed us without an explanation, ought to emerge from the thermodynamics all on its own. The reason behind the rulebook ought to appear. It sounds almost too ambitious to attempt. To derive general relativity, one of the crowning achievements of the human mind, not by studying gravity at all, but by studying heat and information at every point in space. To get the curvature of the universe out of nothing but the counting of hidden states. And yet in 1995, a physicist named Ted Jacobson sat down and did exactly that, in a paper so short and so quietly worded that its full meaning took years to sink in. He treated every point in space as if it had its own tiny horizon, its own entropy, its own temperature, and he asked what would happen if the thermodynamics balanced there the way it does at a black hole. And out of that single assumption, Einstein's equation appeared, like a reason finally stepping out from behind a rule that had stood alone for 80 years. Let us go stand at that point in empty space with him and watch it happen. Part 6. Jacobson turns the key. The move Ted Jacobson made in 1995 is one of the most elegant pieces of reasoning in modern physics. And the wonderful thing about it is that you do not need any equations to follow the logic. You need only 3 ideas, and we already have 2 of them. Let us assemble them slowly, one at a time, because when they click together, the effect is genuinely startling. The first idea we have already met. It is the connection between entropy and horizons. At a black hole, the entropy lives on the horizon and is proportional to its area. Jacobson's first bold step was to say that this is not special to black holes. Any horizon, anywhere, should carry an entropy proportional to its area. And here is the key realization that makes this more than wishful thinking. Horizons are not rare. You can make one anywhere, just by accelerating. To see why, imagine you start running and never stop, faster and faster, accelerating forever. Behind you, there will always be regions of the universe whose light can never catch up to you, because you keep pulling away before their signals arrive. That boundary, the edge of the region from which light can still reach you, is a horizon. It is not made of anything. It is defined entirely by your motion. But it behaves like the horizon of a black hole. It is a one-way surface, a boundary beyond which information cannot cross to reach you. And crucially, every observer who accelerates has one, which means that at every point in space, for a suitable observer, there is a horizon passing through it. Space is quietly full of these potential horizons, one for every possible state of acceleration, waiting to be noticed. The second idea is temperature, and it comes from a result almost as strange as Hawking's, discovered around the same time by a physicist named William Unruh. Unruh showed that an accelerating observer does not experience empty space as empty. They experience it as warm. If you accelerate through the vacuum, through perfectly empty space, with no particles in it at all, a thermometer you carry with you will register a temperature above absolute zero. The faster you accelerate, the warmer the vacuum becomes. This is the Unruh effect, and it is one of the deepest and most disorienting predictions of combining quantum theory with relativity. The vacuum is not a fixed, absolute thing. Whether it looks empty and cold, or warm and full of a faint glow of particles, depends on how you are moving through it. Stand still, and the vacuum is cold and dark. Accelerate, and it begins to hum with heat, a heat directly tied to the horizon that your acceleration creates behind you. The horizon has a temperature, and the temperature is set by how hard you are accelerating. So now we have two of the three ingredients. And notice that they are exactly the two things a thermodynamic system needs. Any point in space, for an accelerating observer, has a horizon. That horizon carries an entropy proportional to its area, and that horizon has a temperature set by the acceleration. Entropy and temperature, the two pillars of thermodynamics, are present at every point in empty space. All that remains is to bring in the third idea and let them work together. The third idea is the oldest and simplest of all, older than relativity, older than quantum theory. It is the basic law of heat that connects these quantities, first written down in the 1800s by studying warmth flowing between ordinary objects. It is called the Clausius relation, and it says something you already understand intuitively. When heat flows into a system, its entropy increases, and the amount of that increase is the heat divided by the temperature. Pour energy into something warm, and you raise its entropy by a predictable amount. That is it. That is the whole law. Heat flowing in, at a given temperature, produces a definite change in entropy. It is the plainest bookkeeping in thermodynamics. The rule an engineer in 1865 would have known. Cold. Jacobson took these three ideas and put them in one place. Stand at any point in empty space-time. Pick an accelerating observer passing through it, which conjures a local horizon. That horizon has a temperature, from Unruh. It has an entropy proportional to its area, from Bekenstein and Hawking. Now let a little bit of energy flow across that horizon, some matter or radiation drifting past the boundary. That energy is heat, crossing into the hidden region. And by the Clausius relation, that heat, at that temperature, must produce a specific change in the horizon's entropy, which is to say, a specific change in the horizon's area. Here is the hinge of the entire argument, so let us say it carefully. The entropy is tied to the area of the horizon. The area of the horizon is a piece of geometry, a feature of the shape of spacetime. So when the Clausius relation demands that the entropy change by a certain amount, it is demanding that the geometry of spacetime change by a certain amount. The flow of energy is forcing the horizon area to change, which means the flow of energy is forcing spacetime to bend. Thermodynamics, applied at a single point, is dictating how spacetime must curve in response to energy. And when Jacobson worked out precisely how spacetime has to curve in order to keep this thermodynamic balance holding true at every point and for every possible accelerating observer, the condition he derived was not something new. It was Einstein's equation, the exact field equation of general relativity, the rulebook that Einstein spent a decade constructing, the relation between curvature and energy that has passed every experimental test for a century, fell straight out of the demand that heat and entropy balance at every local horizon in the universe. He did not assume general relativity, he assumed thermodynamics, and general relativity was the answer. Take a moment to feel how backwards this is from the way we usually think. In the standard story, gravity is fundamental, and its equation is a law of nature that simply is what it is. Thermodynamics is a separate, more approximate business about heat, but Jacobson turned the hierarchy upside down. In his derivation, thermodynamics is the deep principle, the thing you assume, and Einstein's equation is the consequence, the thing you derive. Gravity is not the foundation. Gravity is the output. And Jacobson understood immediately what this suggested, and he said it in words that have echoed through the field ever since. He pointed out that we already know what it means when an equation can be derived from thermodynamics this way. It means the equation is an equation of state. An equation of state is the kind of relation that connects the pressure, volume, and temperature of a gas, the sort of law that describes the bulk behavior of a system made of many small parts, without saying anything about the parts themselves. The gas laws are an equation of state. They are true, they are useful, and they are not fundamental. They are a summary of molecules. So if Einstein's equation is an equation of state, then general relativity is telling us about the bulk behavior of spacetime, the large-scale summary of some underlying system, without telling us what that system is made of. And this leads to the conclusion that reframes the entire 100-year quest. If Einstein's equation is an equation of state, Jacobson wrote, then trying to quantize gravity, trying to find the fundamental quantum particle of the gravitational field, might be a mistake as basic as trying to build a quantum theory of the pressure of air. You cannot quantize pressure because pressure is not a fundamental thing. It is what a huge number of molecules do together. To understand a gas at the deep level, you do not quantize the gas laws. You forget the gas laws and study the molecules, and the gas laws come back on their own as a statistical consequence. Perhaps, Jacobson suggested, gravity is the same. Perhaps the reason gravity refuses to be quantized is that gravity is the pressure, not the molecules. We have been trying to find the quantum of the wrong thing. This should have been front-page news across physics. In a sense, it was recognized as brilliant, and the paper became famous among the people who work on these questions. But it also carried a quiet, nagging weakness, an unfinished edge that kept it from being the final word. Because Jacobson's derivation leaned entirely on that entropy proportional to area. He assumed it, borrowed it from the black hole story, and used it to make everything work. But he never said what the entropy actually was. What system, exactly, has this entropy? When you count the hidden arrangements of the local horizon, what are you counting? Molecules of space? Some deeper structure? The derivation worked, mysteriously and beautifully, without ever answering the question. It was as if someone had derived the gas laws perfectly while refusing to say what a molecule was. The reason behind the rulebook had appeared, and it immediately pointed to a deeper mystery underneath itself. Before we chase that mystery, let us go and stand in the warm vacuum that Jacobson's whole argument depends on, and feel it for ourselves. Part 7. The warm vacuum. Let yourself drift into empty space with me for a moment, far from any star, far from any world, out where there is nothing at all, not a speck of dust, not a stray atom, not a single photon of light. This is the vacuum, in its purest form, the emptiest place the universe can offer. And right now, floating, coasting, moving at a steady pace with no push in any direction, you find it exactly as you would expect. It is cold. It is dark. A thermometer held out in front of you reads as close to absolute zero as anything ever gets. There is nothing here. This is what nothing feels like. Now you begin to accelerate. Something takes hold of you and pushes, gently at first, then harder, a steady increasing force pressing at your back, and you feel yourself gaining speed through the emptiness. And as you accelerate, the impossible begins. The darkness ahead of you is no longer perfectly dark. The thermometer, which read almost absolute zero a moment ago, has begun to climb. The vacuum around you is warming. There is a faint hiss now, a whisper of radiation that was not there when you were coasting, particles appearing out of the empty space as though your motion were coaxing them into existence. You push harder, and the warmth grows. The vacuum that was cold and dead when you were still is now glowing, softly, all around you, a bath of gentle heat that has come from nowhere, from nothing, from the mere fact of your acceleration. You look behind you, back along the direction you have been pulling away from, and you understand where the warmth is coming from. A boundary has formed there, a horizon, trailing you like a wall you are forever outrunning. It is not made of anything. There is nothing there to touch. It is simply the line beyond which light can no longer catch you, the edge of the region that has been cut off from you by your own relentless acceleration. Everything past that line is lost to you now. No signal from beyond it will ever reach you as long as you keep pushing forward. And that horizon, that boundary made of pure motion and geometry, is warm. The heat you feel is its heat. The faint glow filling the vacuum is the radiation of a surface that exists only because you are accelerating. Reach out, in your mind, and let a little energy drift across that horizon behind you, a whisper of radiation slipping past the boundary into the region you can no longer see. And as it crosses, something changes on the horizon itself. Its area shifts, ever so slightly. Written invisibly across that surface is an entropy, a count of hidden arrangements, and the energy you just let fall across it has nudged that count upward, exactly as the old law of heat demands. You cannot see the entropy, you cannot read the ledger, but you can feel that the balance has to hold, that the heat crossing the boundary and the change in its area are locked together by a rule as old as the study of steam, and in that locking together, quietly, invisibly, the geometry of the space around you has bent to keep the books straight. This is the picture Jacobson asks us to take seriously, and once you have stood inside it, the ordinary world never looks quite the same. Because the point of the Unruh effect is not that something magical happens to daredevil observers who accelerate through deep space. The point is far more radical. It is that the vacuum has no single, absolute nature. Whether empty space is cold and empty, or warm and full, is not a fixed fact about the space. It depends on how you move through it. Two observers passing through the very same point of the very same vacuum, one coasting and one accelerating, will genuinely disagree about whether that point is cold and empty, or warm and swarming with particles. And both of them are right. Emptiness itself is not absolute. It is relative to your motion. That should bother you, in the best possible way, because it means the vacuum is not the simple, inert stage we imagine. The vacuum is doing something. It is keeping accounts. It has hidden structure, structure that only reveals itself when you move through it the right way, structure that expresses itself as temperature and entropy on horizons that appear and vanish, depending on who is looking. Empty space, the nothing between the somethings, is quietly full of bookkeeping. And Jacobson's insight was that this bookkeeping is not idle, it is what gravity is. When you demand that the accounts balance at every point, for every observer, the price of keeping them balanced is that spacetime must curve in precisely the way Einstein described. Gravity is the vacuum, keeping its books. Now bring this all the way home, out of deep space, and back into the room where you are. You are not accelerating through the vacuum right now, not in the dramatic way of our thought experiment. But according to Einstein, standing still on the surface of the Earth is a kind of acceleration. The ground is pushing up on you constantly, shoving you off the free-falling path you would otherwise take. And that push is physically identical to the push you would feel accelerating through empty space. This is one of Einstein's oldest and most beautiful insights. The idea that standing in gravity and accelerating in empty space are the same experience, indistinguishable from the inside. Which means that, in a subtle and rigorous sense, there is a faint warmth and a faint horizon associated with you sitting exactly where you are. The vacuum around you is, by an unimaginably tiny amount, warmer than it would be if you were falling freely. You are, right now, an accelerating observer, and the vacuum is keeping accounts on a horizon that belongs to you. The numbers here are so small that you will never feel them, and it is worth being honest about that. The temperature the Unruh effect assigns to ordinary accelerations is fantastically tiny, so far below anything we could measure that no experiment has ever directly detected it. To warm the vacuum by even a single degree, you would need to accelerate at a rate so enormous it is hard to write down. quintillions of times harder than the gentle tug that holds you to the earth. So please do not misunderstand. Nobody is claiming you can feel the heat of the vacuum, or that your chair is measurably warm because of this. The effect is real in the mathematics, and far too faint to sense. But its faintness is not the point. The point is that the machinery is there, running underneath the world, at every point, all the time. The vacuum has a temperature, horizons have entropy, and the balancing of that heat and that entropy, everywhere at once, is enough to reproduce the entire law of gravity. There is a way to make the Unruh effect feel a little less like a magic trick, and a little more like something you almost already understand. Think about how a moving detector interacts with the quantum vacuum. The vacuum is not truly empty in quantum physics. It is a restless sea of fields, forever fluctuating, forever borrowing, and repaying tiny amounts of energy in the smallest allowed instance. When you sit still, those fluctuations average out to nothing, and you register cold, empty space. But when you accelerate, you are constantly changing your relationship to that sea, sweeping through it in a way that never lets the fluctuations quietly cancel. The fluctuations you meet no longer average to zero. They pile up into a genuine thermal glow, a bath of real particles with a real temperature. The heat was not added to the vacuum. It was drawn out of the vacuum's own restlessness by the act of accelerating through it. This is why the temperature depends on your acceleration and on nothing else, and it is why two observers can honestly disagree about whether a patch of space is warm. Heat, here, is not a substance sitting in the space. It is a relationship between the vacuum and the way you move. We have now watched Einstein's rulebook fall out of the thermodynamics of empty space. We have felt the warmth of the vacuum that makes it possible. And we are left standing exactly where Jacobson was left standing, in 1995, holding a magnificent result with a hole in the middle of it. The whole argument runs on the entropy of the horizon. Everything depends on that hidden count of arrangements, and nobody could say what was being counted. It is one thing to know that a ledger is being kept. It is another to know whose ledger it is, and what is written in it. For 30 years, that question sat unanswered at the very center of one of the most beautiful ideas in physics, quietly insisting that the story was not finished. The entropy of the horizon is the entropy of what? Part 8. The question that would not die. There is a particular kind of scientific result that is almost more frustrating than being wrong. It is the result that is clearly, beautifully right, and yet incomplete, in a way you cannot fix. Jacobson's derivation was exactly that. Nobody could find a flaw in it. The logic held. Einstein's equation really did come tumbling out of local thermodynamics. And yet at the heart of the argument was a quantity, the entropy of the horizon, that had been borrowed on trust, its origin unexplained. The whole cathedral was built on a stone whose composition no one could name. Let me make sure the weight of this question is clear, because it is the pivot of everything that follows. Entropy, as we said, is never a fundamental quantity. It is always a count. It is the number of hidden arrangements of some underlying system that all look the same from the outside. When you say a gas has a certain entropy, you are counting the arrangements of its molecules. When you say a deck of cards has a certain entropy, you are counting the orderings of the cards. Entropy without an underlying system to count is a contradiction in terms. It is like being handed a total with no list of items, a sum with nothing being summed. So when Jacobson's derivation, and the black hole formula before it, spoke of the entropy of a horizon, the natural and unavoidable question was, the entropy of what? What is the hidden system whose arrangements this entropy counts? What are the molecules of the horizon? When you write down that a black hole has an entropy proportional to its area, you are implicitly claiming that there are an astonishing number of distinct microscopic configurations that all produce the same black hole from the outside. What are those configurations? What is doing the arranging? The formula gives you the total on the ledger, without showing you a single entry. This was not a trivial or pedantic complaint. It was, and in many ways still is, the central question of quantum gravity. Because if you could say exactly what the entropy of a horizon counts, you would know the microscopic constituents of spacetime. You would know what the universe is made of at the deepest level. The entropy is a census of the hidden pieces, and if you could read the census, you could finally see the pieces. To answer the entropy of what is to answer what spacetime itself is made of. That is why the question would not die. It was not a loose end. It was the whole prize, glimpsed through a keyhole. Over the decades, physicists proposed various candidates, and it is worth naming the direction they kept circling, because it is where the new work would eventually land. A recurring suspicion was that the entropy had something to do with quantum entanglement, with the strange way that the quantum vacuum ties distant regions of space together. Here is the essential idea, stripped down. In quantum physics, empty space is not a collection of independent points. The vacuum is woven through with correlations. What is happening at one point is subtly linked, entangled, with what is happening nearby, in a way that has no counterpart in everyday experience. The vacuum is not a blank sheet. It is a fabric, stitched together by entanglement, every region sewn to its neighbors. Now imagine drawing a boundary through that fabric, a surface dividing space into an inside and an outside, exactly as a horizon does. You have just cut through countless threads of entanglement, the correlations that stitch the two sides together. And when you are confined to one side of the boundary, unable to see the other, those severed threads become a source of hidden information, of missing knowledge, of entropy. The more entanglement crossed the surface, the more information is now hidden from you, and the more entropy the boundary carries. And crucially, this entanglement entropy depends on the area of the boundary, because the severed threads live in the thin region straddling the surface. Area, not volume. The very same scaling that black holes obey. This was a thrilling clue. It suggested that the entropy of a horizon might be entanglement entropy, the hidden information locked behind a surface that cuts through the entangled vacuum. It even reproduced, in a natural way, the mysterious fact that horizon entropy scales with area rather than volume. But it also had a serious problem that kept it from being a clean answer, and the problem was almost embarrassing. When you tried to actually calculate the entanglement entropy across a surface in quantum field theory, the number came out infinite. The vacuum is entangled at every scale, all the way down, and when you add up all the severed threads, including the ones at arbitrarily small distances, the total runs off to infinity. The calculation that was supposed to explain the finite, well-behaved entropy of a horizon instead produced a meaningless infinity. The idea was pointing in the right direction, but it kept overshooting into nonsense. It is worth pausing on how suggestive the area law had become by this point, because it kept showing up from every direction, and in physics, when a strange fact refuses to go away, no matter how you approach a problem, it is usually trying to tell you something. Recall that the entropy of a black hole scales with the area of its horizon, rather than its volume, and that this was already deeply odd. Now the entanglement picture reproduced the same scaling for an entirely different reason, because the severed threads of entanglement live in the thin shell straddling any surface, so the hidden information they carry naturally grows with the area of that surface, and not with the volume it encloses. Two completely separate lines of reasoning, black hole thermodynamics and vacuum entanglement, kept insisting that the information content of a region is written on its boundary, on its surface, rather than filling its interior. This idea grew into one of the boldest proposals in modern physics, the notion that the three-dimensional world we experience might be encoded, in some sense, on a lower dimensional surface, the way a flat piece of film can store a three-dimensional image. We are only going to touch that idea in passing here, because it is a story of its own, but it is part of why so many physicists became convinced that the entropy of horizons was not a curiosity, but a window, and that whatever the entropy was counting, It was counting it on surfaces, in a way that hinted the whole architecture of space might be informational at its root. For a long time, this was where things stalled. The entanglement picture felt right. It connected horizon entropy to the quantum information woven through the vacuum. It explained the area law. And yet it could not produce a clean, finite answer, and it could not by itself close the loop back to Jacobson's derivation and to gravity. There were beautiful pieces on the table, and no one had fit them together into a single, finite, rigorous statement. The question of the entropy of what remained open, decade after decade, a splinter lodged in the foundations of physics. You may already sense the shape of the frustration here. Every advance seemed to answer the question by pushing it down a level. Why is gravity the way it is? Because it is thermodynamics. The thermodynamics of what? Of horizon entropy. The entropy of what? Of quantum entanglement in the vacuum. The entanglement of what? Counted how? Without exploding into infinity. And there the chain would snap. Each answer was real progress, and each answer immediately handed you a new and harder version of the same question. It is a little like opening a series of boxes, each one containing a smaller, more tightly sealed box, and never quite reaching the one at the center. But this is exactly how physics tends to make its deepest advances, not by answering the ultimate question in one stroke, but by sharpening it, by making it precise enough that it finally becomes answerable. And what was needed to sharpen the entropy of a horizon was a better tool for measuring quantum information, a tool that would not choke on infinities, a way to compare quantum states that gave finite, meaningful numbers, even when the raw entropies were infinite. Physicists had exactly such a tool. It had been sitting in the mathematics of quantum information for years, developed for entirely different reasons. It is called relative entropy, and it does not measure how much information a single state hides. It measures how different two states are from each other. And it turns out that when you ask not how much entropy the vacuum has, but how much the entropy changes when you disturb the vacuum a little, the infinities cancel, and what remains is finite, meaningful, and directly connected to energy. That subtle shift from measuring entropy to measuring the change in entropy, from a single state to the difference between two states, is the key that a new paper finally turned. Let us go and watch it turn. Part 9. Comparing Two Universes. To understand what the new work accomplishes, you first need to understand the quiet genius of relative entropy, and the easiest way in is through an ordinary idea, the idea of how surprised you are. Imagine you have a belief about how the world is, and then you learn how the world actually is, and you measure the gap between the two. If reality turns out exactly as you expected, the gap is zero, no surprise. If reality turns out wildly different from what you expected, the gap is large, a great deal of surprise. Relative entropy is, at bottom, a precise measurement of exactly this. Given two states, it asks how distinguishable they are, how much your predictions would be thrown off if you assumed one when the truth was the other. It is a measure of difference, of distance, between two possible descriptions of a system. And unlike raw entropy, which counts the total hidden information in a single state and can run off to infinity, relative entropy compares two states, and in that comparison, the infinities cancel. The parts that are the same in both states subtract away, and what is left is finite, clean, and meaningful. This is the tool the new paper brings to bear on gravity, and the setup is almost startlingly simple. Instead of asking the impossible question, how much entropy does the vacuum have, which gives an infinite answer, the authors ask a humbler and answerable one. Take a small region of empty space. Consider two possible states of it. The first is the pure vacuum, empty space in its ground state, undisturbed. The second is that same region of vacuum with a tiny bit of matter or energy added, a faint breath of something where before there was nothing. Now measure the relative entropy between those two states. How different, in the precise language of quantum information, is the vacuum from the vacuum plus a whisper of energy. And here is where two pieces of mathematics, developed independently, turn out to fit together like a key in a lock. On one side, there is a deep result from quantum field theory. It says that when you compute the relative entropy between the vacuum and a slightly disturbed vacuum in some region, the answer is directly tied to the energy contained in that region, not loosely tied. Precisely equal, in the right setup, to a specific measure of the energy. This connection goes by the name of the first law of entanglement, and it is a rigorous, proven statement about how quantum fields behave. The change in the entanglement of a region and the energy in that region are two expressions of the same quantity. Add energy to a patch of vacuum, and you change how entangled that patch is with its surroundings, by an amount the mathematics pins down exactly. On the other side sits the thermodynamic argument we have already walked through. The entropy associated with a region is tied to the area of its boundary, and a change in that entropy means a change in that area, which is to say, a change in the geometry, the curvature of spacetime. This is Jacobson's insight, now made rigorous, with a properly defined, finite notion of entropy. Watch what happens when you set these two statements side by side. The first law of entanglement says the relative entropy equals the energy. The geometric argument says the same relative entropy governs the curvature. So the energy and the curvature are being connected through the shared quantity of relative entropy without gravity ever being assumed. Relative entropy is the hinge, and on one side of the hinge hangs energy, and on the other side hangs the bending of space. And when you demand that they match, out comes the relation between energy and curvature that we call Einstein's equation. Again, for the third time in this story, from a completely fresh starting point, the rule book of gravity assembles itself out of the accounting of quantum information. Let us stand inside the calculation, and let it be a picture rather than a formula. Imagine you are handed two universes to compare, and both of them look, at first glance, completely empty. In your left hand, a region of pure vacuum, cold and still and undisturbed. In your right hand, the same region, but with a single faint breath of energy added to it, so slight you can barely tell the two apart. Your task is to measure exactly how different they are. You look closer into the fine structure of the vacuum, at the countless threads of entanglement stitching each region together, and you find that the breath of energy in your right hand has subtly changed the weave. The threads are pulled a little differently. The pattern of correlations has shifted. You measure that shift, and it comes out as a single finite number, the relative entropy between your two hands. And now the number begins to speak, and it says two things at once. It tells you how much energy you added, because the first law of entanglement guarantees that the shift in entanglement and the energy are the same thing seen two ways. And in the very same breath, it tells you how the geometry around that energy must bend, because that shift in entropy is a shift in the area of every horizon threading through the region, and area is geometry. One number, the difference between your two hands, simultaneously carrying the energy and the curvature, binding them together. You watch, and out of the comparison, out of nothing but the measured difference between empty and almost empty, Einstein's equation assembles itself in the space between your palms. The relation between matter and the shape of the universe, emerging from a question about how distinguishable two nearly identical vacuums are. There is a reason this particular route succeeds where the older attempts choked on infinities, and it is worth making the reason explicit, because it is the quiet engine of the whole result. When you try to weigh the total entanglement entropy of a region, you have to add up correlations at every scale, all the way down to arbitrarily small distances, and there is no bottom to that sum, so it diverges. But relative entropy compares two states that share the same violent short-distance behavior. The vacuum and the slightly disturbed vacuum are almost identical at tiny scales. differing only in the gentle, large-scale way that a little added energy disturbs them. So when you take the difference between them, the infinite short-distance parts, being the same in both, subtract away and vanish, leaving a finite remainder that reflects only the meaningful, physical difference. It is the same reason you can meaningfully talk about the difference in height between two mountains, even though the height of each above the center of the Earth is enormous and hard to pin down. The shared, unwieldy part cancels, and the difference is clean. This is why the shift from asking how much entropy the vacuum has to asking how much its entropy changes was not a small technical tweak. It was the move that turned an infinite, meaningless quantity into a finite, physical one, and it is what let the entropy of the horizon finally connect to real energy and real geometry without the whole thing exploding. This is the achievement, and it is worth being clear-eyed about exactly what it is and is not. What the authors have shown is that Einstein's equation, the classical law of gravity, can be derived from the behavior of quantum field entropy, using a finite and rigorous measure of that entropy, closing the gap that had haunted the entanglement idea for decades. The infinities that used to wreck the calculation cancel, because relative entropy compares two states rather than weighing one. The result no longer needs to borrow the entropy on trust, the way Jacobson had to. It builds the entropy out of the actual quantum fields of nature, the same fields that describe every particle in the Standard Model, the electrons and quarks and photons that make up everything you have ever touched. The entropy of the horizon is, at last, the entropy of something concrete. It is the entanglement entropy of the quantum fields, measured in the disciplined language of relative entropy. And notice, once more, the single most important feature of the whole thing, the feature that Jacobson flagged in 1995, and that this new work drives home with full force. What comes out of the derivation is Einstein's classical equation, not a quantum theory of gravity, not a graviton, not a fundamental quantum field for gravity. The plain, non-quantum equation of general relativity, the one that describes smooth, curved spacetime, emerges as the large-scale, thermodynamic consequence of the quantum information carried by everything else. Gravity comes out the far side of the calculation already classical, already emergent, already a summary rather than a fundamental thing. It is a bulk description of the quantum fields, in exactly the way that the pressure of a gas is a bulk description of its molecules. So the pieces have finally clicked, the ones that had been lying separately on the table for 50 years. Bekenstein and Hawking gave us the entropy on the horizon and the fact that it scales with area. Jacobson gave us the derivation of Einstein's equation from that entropy, and the crucial suggestion that gravity is therefore not fundamental. And the new work gives us the missing middle, the identification of the entropy as the relative entropy of quantum fields, finite and rigorous, closing the loop. 3 generations of insight, snapping together into a single sentence. Gravity is the thermodynamics of quantum entanglement. Space-time bends because the entropy of the quantum fields demands it. We should let ourselves feel the size of what has just been claimed before we ask the hard questions that remain, because we are going to ask them, and they are serious. But first, sit for a moment with the reframing. For a century we asked how to turn gravity into a quantum theory, and we failed, over and over, and treated the failure as our fault. This work says the failure was the answer. Gravity was never meant to be quantized, because gravity was never fundamental. It is the reason behind the rulebook, and the reason is stranger than the rulebook ever was. Let us finally say plainly why, on this picture, gravity could never have been quantum, and why that changes the deepest goal physics has been chasing for 100 years. Part 10. Why gravity was never quantum. To feel why this reframing matters so much, we need to talk about sound, of all things, because sound is the cleanest example we have of a phenomenon that is completely real and completely not fundamental at the same time. When you hear a note, A pressure wave is traveling through the air. Regions of slightly compressed and slightly rarefied gas moving past your ear. Physicists can describe that wave with great precision. They can talk about its frequency, its speed, its energy. And here is the remarkable part. When you push the description into the quantum regime, sound even comes in discrete packets, little quantized units of vibration. And these packets have a name. They are called phonons. A phonon behaves, in many ways, exactly like a particle. It carries a definite energy. It moves. It scatters off other things. In the mathematics, a phonon looks so much like a fundamental particle that you could be forgiven for thinking it was one. But a phonon is not fundamental, and everyone knows it. A phonon is a collective motion of countless atoms in the material, all moving together in a coordinated pattern. It is a ripple in a crowd, not a member of the crowd. If you took a single atom and asked to see its phonon, the question would be meaningless. A lone atom has no phonon, just as a single molecule has no temperature. The phonon only exists when enormous numbers of atoms act together. It is a real, measurable, particle-like thing that emerges from an underlying system and has no existence apart from it. Sound is not one of the fundamental ingredients of the universe. Sound is what a fundamental system, matter made of atoms, does when its parts move in concert. Now here is the question that reorganizes everything. For 100 years, physicists have assumed that gravity is carried by a particle called the graviton, the gravitational counterpart of the photon, and they have tried and failed to build a sensible quantum theory around it. But what if the graviton is a phonon? What if the graviton is not a fundamental particle at all, but a collective ripple in some underlying system, real and particle-like in the mathematics, yet with no existence of its own? The way a phonon is a ripple in a crystal, and sound is a ripple in the air. If that is true, then the entire century-long failure to build a quantum theory of gravity is not a failure at all. It is a signpost we misread. Consider what would happen if a physicist who knew nothing about atoms tried to build a fundamental quantum theory of sound. They would take the phonon and treat it as an elementary particle. They would try to write down its interactions from the ground up, and they would run into a wall, because sound is not elementary. When you push a theory of phonons to extremely small distances, smaller than the spacing between atoms, it stops making sense, because at that scale, there is no sound, there are only atoms, and the whole idea of a sound wave dissolves. The theory would break down and produce nonsense at short distances, exactly the way every attempt to quantize gravity breaks down and produces infinities at short distances. The parallel is precise, and it is the whole point. Quantizing gravity fails at small distances for the same reason quantizing sound would fail at small distances. In both cases, you are trying to build a fundamental theory of something that is not fundamental. You are trying to find the elementary particle of a phenomenon that is really the collective behavior of a hidden crowd. The infinities are not a mystery to be conquered. They are the theory politely informing you that you have reached the scale where the emergent description runs out, where the ripples give way to whatever is actually rippling. This is why the new work, and the whole emergent gravity picture behind it, is such a profound reframing rather than just another technical result. It does not solve the problem of quantum gravity. It dissolves it. It says the problem was ill-posed from the start. We spent a century asking how to quantize gravity, and the answer is that you should not, because gravity is already the large-scale, classical, emergent shadow of a quantum system, and that system is the quantum fields and their entanglement. You do not quantize gravity for the same reason you do not quantize pressure or temperature or sound. Those things are what a quantum system looks like when you step far enough back that the individual pieces blur into a smooth average. Gravity, on this view, is what the entangled quantum vacuum looks like when you step back far enough to see spacetime. Let me now return to the two phrases I asked you to hold on to at the start, because both of them have quietly turned inside out over the course of this story, and it is worth noticing the reversal. The first was that general relativity is a rulebook, not a reason. For 100 years, Einstein's equation told us exactly how gravity behaves, and never once told us why. That was the great silence at the center of the theory, the missing explanation beneath the perfect description. And now, at last, a reason has arrived. Gravity behaves the way it does because it is the thermodynamics of quantum entanglement. Because spacetime must curve in precisely Einstein's way in order to keep the entropy of the quantum fields balanced at every point. The rulebook finally has a reason underneath it, and the strange, almost poetic twist is that the reason is stranger than the rulebook ever was. We wanted an explanation for gravity, and the explanation we got is that gravity is not really there in the way we thought, that it is a statistical mirage cast by hidden information. The reason did not make gravity more solid, it made it more ghostly. The second phrase was that gravity has no business being warm. When Bekenstein and Hawking first found temperature and entropy lurking in black holes, it felt like a trespass, like thermodynamics wandering into a province where it did not belong, like heat showing up at the door of pure geometry with no reason to be there. And now we can see that the trespass was the whole story. Thermodynamics did not wander into gravity by accident. Thermodynamics is where gravity lives. The warmth of the black hole was not an intruder. It was gravity's true nature, showing itself for the first time. Heat had every business being there, because gravity, all along, was a form of heat, a bulk thermodynamic phenomenon, wearing the disguise of a fundamental force. The thing that seemed most out of place turned out to be the most important clue in the room. Sound and phonons are not the only place this pattern appears, and it helps to know that emergence like this is completely ordinary in the rest of physics, because it makes the claim about gravity feel less like a wild leap and more like a familiar move applied to an unfamiliar target. Water is a smooth, flowing thing with properties like viscosity and surface tension and waves, and none of those properties exist for a single water molecule. They emerge only when trillions of molecules act together, and the equations that describe flowing water were written and used for a century before anyone knew molecules existed at all. In modern materials, physicists routinely deal with particle-like objects that are pure emergence. There are ripples in magnetic materials that behave like particles, disturbances in electron seas that carry a fraction of an electron's charge, collective excitations of every kind that walk and talk like fundamental particles and are nothing of the sort. Physicists even have a name for this whole category. They call them quasiparticles, real and measurable and particle-like, yet made entirely of the coordinated behavior of a hidden crowd. The lesson of the last century of physics is that a great deal of what looks fundamental, when you look closer, turns out to be the collective song of something smaller. The genuinely new and startling suggestion is only which thing we are now pointing this old lesson at. Not sound, not water, not a magnet, but space-time itself, and the force that shapes the entire universe. It is worth stepping back and appreciating how rare this kind of reversal is in science. Usually progress means adding a new piece, finding a new particle, refining a number. Only occasionally does progress mean discovering that something you thought was a foundation is actually a facade, that a floor is a ceiling, that a fundamental thing is emergent. It happened when we learned that heat is not a fluid but the motion of molecules. It happened when we learned that the fixed stars are other suns. And it may be happening now, with gravity, the oldest and most trusted force of all, quietly revealing itself to be the surface expression of a deeper layer made of quantum information. I want to be careful and fair here, because this is a place where excitement can outrun the evidence, and this channel does not do that. What has been shown is that Einstein's equation can be derived rigorously and with finite quantities from the relative entropy of quantum fields. That is a genuine and beautiful mathematical fact. Whether that fact means gravity truly originates in entropy, or whether it means only that gravity can be described this way among other ways, is a question we will take up honestly in a moment, because serious physicists disagree about it. A mathematical equivalence is a powerful hint, but it is not the same as a proof of origin. We will hold both the wonder and the caution together, the way the best physicists do. But before we test the idea against its own limits, I want to bring it all the way down from black holes and vacuums and quantum fields into the one place where it becomes impossible to keep at arm's length. Because if this picture is right, then it is not only black holes and distant galaxies that are made of thermodynamic bookkeeping. It is you, the weight in your own body, the pressure of the seat against you right now, the heaviness you have carried and felt every single day of your life is, on this view, the visible total of a hidden ledger you can never read. Let us go there, gently, and feel what it means to say that your own weight is information. Part 11. Your weight is information. Feel your own weight for a moment. Really feel it. The press of the chair against you, or the floor against your feet, or the mattress along your back. That steady downward heaviness that has been with you every second since you were born, so constant that you almost never notice it, the way you never notice the air. It is the most physical sensation there is. There is nothing abstract about it. It is the plainest, most bodily fact of your existence, the simple truth that you have weight and the ground holds you up. And yet, if the picture we have been building is right, that heaviness is not what you think it is. It is not a fundamental force reaching up from the center of the earth and pulling on your body. It is the visible surface of a calculation. It is the running total of a ledger written in the entanglement of quantum fields, a bookkeeping of hidden information that you can feel in your bones but can never read with your eyes. Your weight is information made heavy. Let me try to make that concrete, because it is easy to say and hard to feel. Watch an apple fall from a branch. In the old picture, Newton's picture, a force reaches out from the earth and pulls the apple down. In Einstein's picture, the earth has bent the spacetime around it, and the apple simply follows the natural curve, coasting along the straightest available path into the ground. Both pictures are useful, but now look one level deeper into the picture this new work suggests, and watch the same apple fall a third way. There is no force pulling the apple. There is no invisible cord. Instead, all around the apple, threaded through the empty space it moves through, is the quiet accounting of the quantum vacuum, the entanglement of the fields, the hidden entropy, written on every horizon that passes through every point. And the presence of the earth, all that mass and energy, has tilted that accounting. It has made one direction through spacetime cheaper than the others, in the currency of entropy, in the bookkeeping of information. The apple does not fall because something grabs it. The apple falls because falling is the path that keeps the ledger balanced, the route that lets the entropy of the fields increase the way it must. Spacetime bends toward the earth because the quantum information demands it, and the apple, following the bent geometry, drifts down along the cheapest accounting line the universe offers. The fall of the apple is bookkeeping made visible. It is the settling of a vast, invisible sum, expressed as a small red fruit meeting the grass. Now turn that same lens on yourself, sitting there, held in place. The pressure you feel is your body being prevented, by the solid ground, from following its own cheapest accounting line into the earth. You are leaning against the ledger. Every ounce of your weight is the felt resistance of a calculation you are inside of, a calculation running underneath the world at every point, all the time, silently balancing the entropy of the quantum fields, and expressing the result as the heaviness in your limbs. You are not being pulled. You are reading the total of a hidden sum through the only instrument you have, which is your own body. There is something both dizzying and strangely intimate about this. Dizzying because it takes the most solid, trustworthy sensation you own and reveals it to be abstract, informational, a shadow of numbers you cannot see. Intimate, because it means that the deepest machinery of the universe is not somewhere far away, in a distant black hole, or the first instant of the cosmos. It is right here, in the ordinary weight of your own hand, resting on your own knee. You do not have to travel to the edge of a black hole to touch the thermodynamics of spacetime. You are touching it constantly. You have been touching it your whole life. Every time you have felt heavy, every time you have climbed stairs or lifted something, or simply sat down, tired, at the end of a long day, you have been feeling the entropy of the quantum fields keeping its accounts. The exotic and the familiar turn out to be the same thing, and the most cosmic fact in physics is pressing against you at this exact moment. I want to be honest that this is the part where a careful listener should feel two things at once, and both are appropriate. The first is wonder, and I hope you are feeling it, because it is earned. The second is a healthy caution, and I want to name it rather than hide it. When I say your weight is information, I am describing what this picture implies if it is correct, and I am describing it in the most vivid way I can, because that is how you feel an idea in your body, rather than just filing it in your head. But the picture is not settled science. It is a serious, rigorous, and growing body of work that reframes gravity as emergent, and it has real evidence behind it, the derivation of Einstein's equation from quantum field entropy, chief among that evidence. It is not a wild speculation, but neither is it a closed case. So hold the wonder and the caution together. Let yourself feel the vertigo of your own weight becoming information, and also keep the quiet awareness that physics is still arguing about whether this is the final truth or a beautiful piece of a truth not yet complete. Because here is what makes even the caution wondrous rather than deflating. Even the most skeptical physicist, the one who insists we have only shown that gravity can be described this way, and not that it must originate this way, agrees on the core mathematical fact. Gravity can be written in the language of thermodynamics and quantum information. That much is no longer in doubt, and that fact alone, whatever its ultimate interpretation, is trying to tell us something. When the most fundamental seeming force in the universe keeps insisting on being written in the language of heat and hidden information, over and over, from black holes to accelerating observers to the relative entropy of the vacuum, at some point you have to listen. Something about gravity wants to be understood as information. It has been saying so for 50 years, in every language we have tried, and it has never once contradicted itself. So sit with your own weight a little longer, differently now. That heaviness you have carried your whole life, without ever questioning it, may be the single most direct contact you will ever have with the deepest layer of reality. Not a metaphor, not a poetic flourish, the actual claim of actual physics, that the pressure of the seat against you is the surface of a hidden ledger, and that you have been reading the universe's most fundamental bookkeeping every day of your life, without knowing it, through the humble sensation of being heavy. The floor beneath you has not moved an inch, but what it means to be held up by it has quietly, completely changed. And having come this far, having let gravity dissolve from a fundamental force into the thermodynamics of quantum information, having felt our own weight become a ledger, we finally arrive at the question this whole journey has been carrying toward the end. Because there is one thread we have not yet pulled, the deepest and most honest one, the question that every version of this idea has run into, and that the new work, for all its beauty, does not escape. We have learned that gravity emerges. But emerges from what? We have learned to read the totals on the ledger, but we still do not know what is being counted. Part 12. Emerges from what? Before we stand at the edge of the final question, we owe the idea a fair trial, because a claim this large attracts both careless enthusiasm and careless dismissal, and the truth lives between them. Let us take the objections and the misreadings honestly. one by one, the way a good physicist would. Start with the fringe, because it is the easiest to clear away. Whenever people hear that gravity might not be a fundamental force, someone concludes that we can therefore switch it off, that anti-gravity is around the corner, that free energy is hiding in this idea somewhere. It is an understandable leap, and it is completely wrong, and the reason is simple. Emergent does not mean fake, and it does not mean optional. Temperature is emergent, a mere summary of molecular motion, and yet you cannot wish a fire cool, and you cannot reach in and switch off the heat by declaring it non-fundamental. Pressure is emergent, and it will still crush a submarine. Emergent phenomena are every bit as real, every bit as binding, and every bit as unforgiving as the things we call fundamental. Calling gravity emergent gives no one a lever to turn it off. There is no loophole here, no hidden free lunch, no engine that runs on the news that gravity is thermodynamic. The apple still falls. The idea reorganizes what gravity is, not whether it holds you down. A second, more serious misreading is that mainstream physics is somehow hiding this, that there is a suppressed truth, that gravity is an illusion. There is nothing hidden. This work is published in the open, argued about at conferences, praised by some and doubted by others, and its own authors are the first to list what it has not yet solved. And the claim was never that gravity is an illusion. An illusion is something that is not there. Gravity is absolutely there. The claim is that gravity is real and emergent, rather than real and fundamental. And those are very different statements. The heat of a fire is not an illusion just because it emerges from molecules. It will still burn you. Gravity is not an illusion just because it emerges from information. It will still hold a galaxy together. Then there is a genuinely respectable rival strand of this story, and honesty requires that we give it its due, rather than pretend the emergent gravity idea is only ever profound and clean. Some physicists have taken the notion that gravity is entropic and pushed it in a bolder, more testable direction, proposing that if gravity really is emergent, then on the largest scales, across whole galaxies, it might not behave exactly as Newton and Einstein predict. It might deviate in a way that mimics the effects we normally attribute to dark matter, the unseen substance we invoke to explain why galaxies rotate faster than their visible matter should allow. If gravity itself changes character on galactic scales because of its entropic nature, perhaps there is no dark matter at all, only gravity behaving in a way we did not expect. This is real science, taken seriously by serious people, and it has had a mixed record. It has scored some suggestive successes and run into some real difficulties against the detailed observations, which increasingly favor actual dark matter for many phenomena. I mention it not to endorse it, but to be fair. The emergent gravity idea is not a single tidy theory. It is a family of ideas, some rigorous and modest, some bold and contested, and an honest account holds them at their true weights. And finally, there is the deepest and most legitimate scientific caution of all, the one raised by careful physicists who admire this work and still withhold the final verdict. It is this: to show that Einstein's equation can be derived from the relative entropy of quantum fields is a magnificent mathematical fact, but a mathematical equivalence is not automatically a statement about origin. That gravity can be described in the language of thermodynamics does not, all by itself, prove that thermodynamics is where gravity comes from. Two things can be mathematically equivalent without one being the cause of the other. So there is a spectrum of honest opinion. At one end, physicists who read this as decisive, who believe gravity is now shown to be emergent, and the century-long quest to quantize it was aimed at the wrong target all along. At the other end, physicists who read it as a beautiful reformulation that has not yet earned the word origin, a striking way of rewriting gravity that may or may not reflect its true source. And in the middle, the synthesis that nearly everyone can accept, that it is now simply a mathematical fact that gravity can be written in the form of thermodynamics and quantum information, and that this fact, whatever its final interpretation, is remarkable and demands to be understood. Hold all of that, and now step to the edge, because underneath every reading, optimistic or cautious, there sits one question that none of them can answer, and it is the question this entire journey has been walking toward. If gravity emerges, then it emerges from something. That is what emergence means. Temperature emerges from the motion of molecules. Pressure emerges from their collisions. Sound emerges from the coordinated dance of atoms. In every case, the large-scale thing is a summary of smaller things, and when you ask what the smaller things are, you can answer molecules, atoms, particles. But when we ask what gravity emerges from, the new work gives us an answer that is real progress, and also, maddeningly, not the end. It says gravity emerges from the entropy of quantum fields. And entropy, remember, is always a count of hidden arrangements of some underlying system. So the question simply steps down one level and asks itself again, sharper than before. The entropy of the quantum fields counts the arrangements of what? What are the ultimate microscopic pieces whose bookkeeping we experience as the curve of spacetime and the weight of our own bodies? Strings vibrating in dimensions we cannot see? Some granular structure of space below the Planck length, that scale 10,000 trillion times smaller than an atom where our current physics simply stops? Some structure with no name yet, no picture, nothing we have ever imagined, waiting one level below the fields we thought were the bottom. We do not know, and I want to say that clearly, without flinching and without dressing it up, because it is the honest truth, and it is the most important sentence in this whole story. We do not know what gravity ultimately emerges from. The new work answered the entropy of what with the entropy of quantum fields, a genuine and hard-won advance. And in the very same motion, it handed us the next of what, deeper and harder than the last. This is the question every version of emergent gravity has circled for 50 years, and it is still open, still glowing quietly at the center of the mystery, unanswered. And here is the thing I most want you to carry away as you drift off tonight. The mystery is not that gravity is unexplained. We have explained a great deal. The mystery is that the more precisely we explain it, the more clearly it points beyond itself, to a hidden layer of reality we have never seen and do not yet know how to describe. We started this journey standing on gravity, as if it were the solid floor of physics, the deepest thing there was, and we have watched that floor turn transparent and reveal beneath it the thermodynamics of quantum fields, and watch that in turn hint at yet another floor below and another shape in the dark beneath that. Every answer has been a door, and behind every door has been a larger room. We have learned to read the totals of a ledger without yet knowing what is being counted, and somehow that is more astonishing than a tidy answer would ever have been. A finished explanation would close the book. This one keeps opening it. There is a particular kind of peace in that, if you let there be. For most of history, the fear was that science would one day explain everything and leave the universe small and known and drained of wonder, a machine fully mapped. And here, at the foundation of physics, at the origin of the most familiar force in your life, we find the opposite. We find that the closer we look, the deeper it goes. We find that the weight in your own body opens onto black holes, and black holes open onto the entropy of the vacuum, and the entropy of the vacuum opens onto a layer of reality that has no name yet. The apple falls, as it always has, as it did before anyone watched, and as it will long after. But now, when you watch it fall, you are watching the surface of something without a bottom, the visible total of an invisible sum, the universe quietly keeping accounts in a language we have only just begun to read. Gravity was never the floor, it was a window, and we are only now beginning to see how far down the view goes.